we're going to take a look at section 6.3, number 25. We've got a nice little proof here. We're given a triangle ADBEC. So we've got triangle ABC and triangle DBE. We're told that DE is parallel to AC, so let's fill that in. These guys are parallel, and we need to show that length AD divided by length DB, so the ratio of these two sides is equal to CE divided by EB, the ratio of these two sides. Okay, how are we going to handle this? Well, recall that we were given that DE is parallel to AC. So that means that triangle ABC is similar to triangle DBE. That was theorem 6.10. Okay, now this theorem doesn't just give us that these two guys are similar. If you look at the theorem, it also gives you a nice little proportionality thing here. Unfortunately, the proportionality that we get is AB divided by DB is equal to CB divided by EB. Okay, why is that unfortunate? Well, that's not what we're looking for. We're looking for AD. We're looking for this little part here. And all we have to work with is the entire thing. Likewise, we have this little part over here, and all we have to work with is the entire thing. AB. That segment AB is equal to AD plus DB, the sum of the two smaller segments. Likewise, on this side, the long segment BC is equal to the sum of the parts BE and EC. I think we can use this to our advantage. And the big thing here is that the parts that we want, say AD, we want this. DB, the leftover bit that we don't want, we want to get rid of. Hey, look, that's the denominator right there. So that's going to help us out here. We want to take AB and subtract DB. Now we can't just subtract it willy-nilly, but the fact that it's the denominator is going to help us out a lot. We'll take AB, DB, and I'll subtract 1. And that's going to still be equal to my right-hand side, so long as I subtract 1 from that side too. Why 1? Well, you know, DB divided by itself is equal to 1. Likewise, EB divided by itself is equal to 1. So now we have CB divided by EB over here, and AB divided by DB over here. And the wonderful thing here is common denominator, we can subtract. So the numerators will be AB minus DB, all divided by DB. And this numerator will be CB minus EB, again, all divided by EB. And what was AB minus DB again? Oh yeah, that's right, it was AD. That's what we were looking for. AD divided by DB. We were looking for that ratio to be equal to CB minus EB. That's CE, remember, divided by EB. That ratio. So we're done. Yay, indeed. Okay, one last problem I want to take a look at. Section 6.3, number 29. Another proof. All right, now, in this case, we're given this odd shape, and we are told that line segment BE bisects angle ABC. So we're going to take a note of that. We're going to say that this angle right here, ABE, is congruent to this angle over here, EBC. These guys are congruent. We also know that AB divided by BE, the ratio between AB and BE, is equal to the ratio between BD and BC. And what we need to show is that angle A right here is equal to angle D right here. We need to show this. To show. Alright, where are we going to start? Well, a good place to start would be to get some congruency going. So we were given that the ratio between AB and BE is equal to the ratio between BD and BC. And then we were also, now what I want to do with that is set it up in a more common form where I've got this triangle here, this length here, AB, BE. This is going to be one of our triangles that we're going to be looking at. As we've got the stuff for this triangle. That's one of the ones where we want to get similar. And then the other triangle I want to take a look at is over here. It's going to actually be the triangle BDC. That's the other triangle we want to take a look at. And a lot of time we say, okay, AB divided by BD. We set up a ratio between the two triangles, not a ratio within the triangle itself, like AB and BE. So we're going to flip these ratios around a little bit. And I want AB divided by BD to be equal to BE divided by BC. And we can do that either using cross multiplication or simply writing, hey look, this was part of theorem 6.2. Tells us all the different ways when we have this proportionality set up, we can change it around. Okay. Next, recall that we had BE bisecting ABC. And that means that we've got some angle congruencies, namely angle ABE is going to be congruent to angle CBD. When we say something bisects, when we say a line segment bisects an angle, it's into two equal parts. So we've got congruent angles, we've got proportional sides. That means we've got similar triangles. Recall again that the sides that we had similar was this one, AB, similar to this guy, BD, and BD, the full length. And then we had BE, the short length, being proportionate to BC. So if we draw out these triangles, we get, and that really helps you see what's going on here. We've got right here triangle A, B, E, and then I've got triangle B, D, C. I've got these angles congruent, this side proportionate, this side proportionate. So that is going to give us similar triangles. Now we want to be very careful with the order in which we write this. So I'm going to say ABE. ABE. And what's that going to be similar to? The correct ordering of the letters is D, B, C. Recall we went 1, 2, 3, so we have to go 1, 2, 3. That order is important. And this is by the side angle side similarity. Well, we got two similar triangles. That means that, say, this angle right here, angle A, is going to be congruent to this angle right here, the corresponding angle, D. Because in similar triangles, all the angles are congruent. So we could say this is by the definition of similarity. That's what we set out to prove. So this proof is complete.